Andromeda is visible tonight. If you know where to look, if you are in the northern hemisphere on a clear night, far enough from city lights, you can see it without a telescope. A faint smudge in the constellation Andromeda, a small blur under the great square of Pegasus, so soft that many people mistake it for a thin cloud. It does not look like a destination. It looks close enough to ignore. But that smudge is a galaxy. Hundreds of billions of stars, perhaps a trillion. Stellar nurseries, dead suns, black holes, planets we will never count, civilizations that may have risen and vanished without ever knowing our galaxy existed. A complete continent of light. And it is about 2.5 million light years away. That number is where the dream begins to fail. Because Andromeda is not merely far. It is far in a way that breaks the human idea of travel. It is close enough for its light to reach our eyes. Close enough for our telescopes to map its spiral arms. Close enough that gravity is pulling it toward the Milky Way. And still, within the physics we understand, no ship we can build from matter, energy, engines, shielding, and time will reach it as a journey in any human sense. Not because we lack courage. Not because our rockets are primitive. Because the universe is not sized for us. Start with the fastest thing we have ever made. Parker Solar Probe, diving close to the Sun, has reached roughly 430,000 miles per hour, about 690,000 kilometers per hour. It is the fastest human-made object in history. At that speed, it could cross the United States in seconds. It moves so fast that every ordinary machine on Earth seems motionless beside it. And it is still only about 0.06% of the speed of light. At that speed, if it could somehow point toward Andromeda and keep that velocity forever, the trip would take almost 4 billion years. 4 billion years. That is not a voyage. That is a geological age larger than the entire history of complex life on Earth. Oceans would move. Continents would fuse and break apart. The sun would brighten. Species would rise, dominate, vanish, and be forgotten. The civilization that launched the craft would not merely be dead, it would be erased from context. And even that estimate is generous, because Parker Solar Probe does not cruise through deep space at that speed. It reaches it by falling through the sun's gravity well during close approaches. A ship to Andromeda would need to accelerate, protect itself, navigate for millions or billions of years, and somehow still be a ship at the end. The first lesson is simple. Our fastest spacecraft is not slow because our engineers failed. It is slow because light is almost impossibly fast. So we ask the obvious question: why not go closer to light speed? If you enjoy cosmic thought experiments where the real universe turns out stranger and harsher than science fiction, subscribe to the channel. We are going to keep walking into questions like this, the ones where the answer is not that we need a better engine, but that reality itself has a price. Imagine a ship moving at 90% of light speed. Now the numbers feel heroic. Andromeda is 2.5 million light years away. So from the outside universe, even a ship moving at 90% of light speed still takes almost 2.8 million years to get there. That is already a problem. But relativity gives the travelers a strange gift: time dilation. For the moving ship, time passes more slowly than it does for the galaxies around it. At 90% of light speed, the crew would experience less time than the outside universe. At 99% of light speed, the effect becomes stronger. The outside journey still lasts about 2.5 million years. But the crew experiences roughly 360,000 years. 360,000 years. Longer than the entire history of our species. At 99.9999% of light speed, 6 nines after the decimal, the crew would still experience thousands of years of travel. Not days, not decades, thousands of years. The ship would need to be not just a spacecraft, but a self-contained lineage. A civilization wrapped in shielding. A moving world with agriculture, repair systems, genetic continuity, political stability, medicine, memory, and purpose, all preserved longer than recorded history has existed. And that is before we ask how it gets up to speed. Relativity does not merely make high speed strange. It makes it expensive. The closer a massive object gets to light speed, the more energy it takes to push it faster. Not a little more. Not linearly more. The requirement climbs without limit. To reach light speed exactly would require infinite energy, which means no ship made of matter can ever do it. But even stopping short is brutal. A 100-ton spacecraft is tiny by science fiction standards. Smaller than many aircraft. Smaller than many ships on Earth. But accelerating even that modest payload to 99% of light speed would require energy on a scale that belongs to civilizations far beyond our own. And if the ship has to slow down at Andromeda, the energy problem doubles in spirit before the engineering even begins. Rockets make the problem worse. A rocket must carry the propellant it uses to accelerate. But propellant has mass. That mass must also be accelerated, which requires more propellant, which adds more mass. The equation does not grow politely. It grows exponentially. Chemical rockets fail immediately. Nuclear rockets fail less embarrassingly, but still fail. Antimatter sounds like the perfect answer because matter-antimatter annihilation converts mass into energy with extraordinary efficiency. But antimatter is not magic. It must be produced, stored, aimed, controlled, shielded, and used without destroying the ship it is supposed to push. Humanity has made amounts of antimatter so small they are measured in particles and nanograms, not fuel tanks. And even ideal engines do not remove the next problem. Space is not empty. Between the stars, there is gas. Thin gas. Almost nothing by Earth standards. Sometimes only about 1 atom in a cubic centimeter. You could call that vacuum and be right in almost every ordinary situation. But at relativistic speed, almost nothing becomes something. A hydrogen atom sitting quietly in interstellar space is harmless. A hydrogen atom hitting a ship at 99% of light speed is not harmless. In the ship's frame, that atom arrives like a particle from an accelerator. It can ionize matter, damage materials, break chemical bonds, produce radiation, and it does not happen once. It happens continuously across the entire front of the spacecraft for millions of years of external travel. Dust is worse. A microscopic grain, invisible and insignificant at ordinary speeds, becomes a bullet carrying catastrophic energy. A larger grain becomes a bomb. The ship would need a shield thick enough to survive not one impact, but a universe full of small impacts arriving with particle accelerator violence. The shield adds mass. Mass increases the energy required. More energy requires more fuel or more external power. More fuel means more mass. Every solution makes the original problem heavier. This is why Andromeda is so different from Mars or Pluto or even the nearest stars. In the solar system, distance is mostly an engineering problem. Across interstellar space, distance becomes a civilization problem. Across intergalactic space, distance becomes something closer to a cosmic law. And Andromeda is not across the Milky Way. It is across the gap between galaxies. The Milky Way is about 100,000 light-years wide. That is already enormous. But Andromeda is 25 times farther away than the width of our entire galaxy. The darkness between us is not a road. It contains no fuel depots, no rescue points, no stars to pass near for warmth or resources. For almost the entire journey, the ship would be alone in intergalactic space, moving through thin gas, dust, radiation, and time. If a future civilization built such a ship, what would it really be? Not a mission, a departure. The crew would not be explorers in the usual sense. They would be immigrants from history. Even at relativistic speed, even with time dilation, even with technology beyond ours, they would leave behind every nation, every language, every living connection, every argument and memory of the world that launched them. By the time they reached anything recognizable as Andromeda, Earth would be unimaginably changed. The Milky Way itself might be entering a new gravitational future. There is another twist. Andromeda is coming toward us. For years, the standard picture has been that the Milky Way and Andromeda will make their first close approach in about 4 to 5 billion years and eventually merge into a larger galaxy. Newer simulations add uncertainty to the exact future because the motions and masses of other local group galaxies matter. But the basic point remains. Andromeda is not a fixed island waiting patiently in space. It is moving. We are moving. The local group is a gravitational dance, not a map with pins stuck into it. A slow ship does not travel to the Andromeda we see tonight. A fast ship does not escape the price of being fast. And a perfect light-speed ship cannot exist if it has mass. That is the trap. The galaxy is visible. The destination is real. The path is physically imaginable. But the act of sending a meaningful ship there collapses under energy, shielding, time, and identity. We can send light. We can send radio waves. We can send mathematical descriptions if someone there is listening 2.5 million years from now. But a ship is different. A ship carries matter. Matter has inertia. Matter needs protection. Matter ages. Matter fails. Matter cannot ignore the speed of light, the rocket equation, or the quiet violence of the gas between stars. And beyond Andromeda, the universe becomes even less forgiving. Most galaxies are not gravitationally bound to us. The expansion of space carries the distant universe away. On the largest scales, dark energy makes that expansion accelerate. Galaxies beyond our local gravitational island will eventually pass beyond any possible reach, not because they move through space faster than light in the local sense, but because the space between us and them grows faster than any signal can cross. There are places in the universe that are not merely far. They are permanently unreachable. Andromeda is crueler, in a way, because it is not in that category. It is nearby by cosmic standards. It is part of our local group. It is visible to the naked eye. It is approaching us. It is one of the most reachable galaxies in existence, if the word reachable is allowed to mean anything at all beyond the Milky Way. And even this nearest great spiral breaks the idea of travel. That is what makes it frightening. Not that Andromeda is impossible, because it is exceptional. That it is impossible even though it is one of the best cases. If humanity ever builds ships capable of crossing interstellar space, Alpha Centauri will be an achievement. Nearby red dwarfs will be frontiers. The Milky Way itself, after millions of years, might become a slow ocean of possible journeys. But Andromeda remains something else. Not the next city. Not the next continent. Not even the next shore. A different island of stars, visible across a gulf that light can cross, but civilizations cannot easily survive. So here's the question. If a future civilization had the power to build one ship aimed at Andromeda, a ship that would never return, whose crew would never see home again, whose arrival would matter only to descendants thousands or hundreds of thousands of years removed from the launch, should they build it? Would you support a mission like that, knowing it might be the greatest act of exploration ever attempted, and also the most permanent goodbye any civilization could make? Leave your answer below, because this is one of those questions where physics gives us the limits, but humanity still has to decide what the limits mean. Look up tonight and find Andromeda. The light entering your eyes began its journey before modern humans existed. It crossed intergalactic space without engines, without fuel, without shielding, because light is allowed to do what matter is not. It simply moved at the one speed the universe gives freely to massless things. A ship is not light. A ship has weight, structure, people perhaps, or machines that carry the signatures of people. It has to pay for every meter with energy, survive every atom it meets, and carry its purpose through a duration longer than civilizations can remember themselves. That is why the smudge in the sky matters. It shows us something we can see but not possess. A galaxy close enough to be familiar in photographs, close enough to name, close enough to watch approaching, and still too far for any journey we can honestly call a journey. The universe is not cruel about this. It is not trying to keep Andromeda away from us. It simply has the scale it has, and the physics it has. And in that physics, distance is not empty. Distance is time. Distance is energy. Distance is radiation. Distance is everything a ship must endure before arrival becomes more than a word. Andromeda is visible tonight. The stars in it are real. The worlds in it may be real. The distance is real. And the distance is everything.